So it's a mouse model with controllable pigmentation. So the have no related disclosures. The purpose of the mouse model is to determine light dose for laser treatment, which is arguably the most important parameter for laser therapy. Here shows one case is from a publication here. The light dose is too high, not safe, so cause significant scab and later hypopigmentation. So we want to warn this, but we don't want to use too low laser dose, which is not achieve the therapeutic effect you desired. So in the past, we did study, basically irradiated the skin with insulating light dose. You can see different effect. Some is too safe, some is too high. And we don't want to do this to hurt people. So we have, with my collaborator from University of Kentucky, of this mouse model. The key of this is, first, we want to have a humanized model which has the stem cell factor in the epidermis. So basically, it's melanin throughout the skin, not only in hair follicles, which is different between mouse and human. You can see it's totally dark. It's not exactly what we desired. So we have this receptor defect. It can only generate eumelanin. It looks like pink. The final step is if we apply force clean daily, this has the pigmentation can be changed. It depends on the day's application. You can see here from pink and measured reflecting parameter decrease from kind of like skin type 1 to skin type 5. So from this, we can use this mouse. You see there are couple spots we can use for irradiation. The light dose increase from 10 to like 18 before and after irradiation. We can see this is 1 day after irradiation. The circled part, the yellow circle, you can see there are scabs, which can be seen when the dose is higher than expected. The surprising thing is you can see the circle in the lower panel at day 7 is even there's no significant pigmentation, we saw hypopigmentation occurred. That is some surprise to us, which is the characteristic of this mouse model we later realized. So for the top panel, day 1, we can see the immediate effect of the laser. Basically, that part can be used for determine response of how human skin responds to laser irradiation. The longer time, like day 7, that is a little bit different, maybe used for other applications. So the reason is for this particular mouse, after the melanosome got damaged, it removed by the body's autophagy system. Because we stop apply force clean, there's no generation of new melanosome with eumelanin. So it won't be able to get darker. But we confirmed with further experiment the melanocyte not damaged. So which means we apply force clean again, then we can got repigmentation. So that's the part of the pigmentation. So then we can separate the damage of melanosome with regeneration of melanosome. In human, you cannot separate this. For this mouse model, we can separate this. So we did further experiment, IR temperature measurement during irradiation. You can see from the finger, with higher dose, it reached 90 degrees. For lower dose, it reached 70 degrees. So for this, clearly shows for higher temperature, higher dose, there's a depigmentation, hypopigmentation. For the lower, it's not there. So this mouse, you can change the pigmentation, which the absorption coefficient of the skin can change. So it can also be used to verify optical technique to measure optical skin properties, such as SFDI. So here, this is the result measured by SFDI. For scattering, for absorption, there's no surprise. Decrease with wavelength, increase with pigmentation, but there is some interesting thing against physics for the scattering coefficient measured using this instrument, the data can be used to validate other technique. Okay, so I finished 509. That's my conclusion. Thank you.